Hello, and welcome to a lecture on cylindrical parabolic antenna, physical optics. So first, cylindrical reflectors. What is a cylindrical reflector? It looks like this. It's parabolic in one plane, and it is a cylindrical extrusion in the other plane. So it looks like this. So if you look at it from the side, it's a parabola. If you look at it from the front, it's a planar aperture. Such a thing is normally fed with a line feed. And line feed is at the focus of the parabolic reflector, here and here and here. And you can understand the pattern that this makes by looking at what happens in each of these two planes. So in this plane, the plane of the parabola, you get the pattern that you'd expect from a parabolic antenna. And over here, you get what you'd expect from a line source. So you get different patterns in different planes. Generally, the beam in the plane of the parabola is relatively wide, and the beam in the other dimension is relatively narrow. And that's because this dimension is typically less than this dimension. And that results in a fan beam. So applications of these types of reflectors, well, one is air surveillance radar. So perhaps you've been in an airport and you've seen an antenna like this. It's usually rotating. In this cut, you have elevation, and in the other cut, you have a very narrow slice of azimuth. So this is kind of what you want for a ground-based aviation radar. Radio astronomy, this appears because it's a simple way, mechanically simple way to construct a very, very large antenna. So such antennas might be used in things called transit instruments, which are steerable only in one direction by rocking the parabola back and forth. Another reason for considering cylindrical reflectors, aside from their applications, is that they can be viewed as a two-dimensional prototype for a three-dimensional paraboloidal reflector, facilitating insight that might be difficult to achieve in the more complex three-dimensional case. Said differently, you can think of a cylindrical reflector as being a 2D version of a three-dimensional paraboloidal reflector, and it's somewhat simple to analyze this 2D case. So you could work through some design options in 2D and then go to 3D when you're ready, and then bring in the complexity only after you've sketched out the basics of the design. Okay, an overview of this lecture. First, a problem statement. Then we'll derive the physical optics integral because we will analyze the example using physical optics, show you the results, and then a few concluding remarks about what we've found. So here's the problem statement. By the way, this is from your textbook, the 2013 version of Stutzman and Thiel, section 16.6. It's used to demonstrate UTD, actually, but it can also be analyzed using physical optics. I should say your book actually does not show physical optics. It shows geometrical optics aperture integration. So if you want to see how to analyze this reflector using geometrical optics aperture integration, then there is a place to do it. I'm going to use physical optics. In any event, we have a coordinate system, x and y, as we are prone to use in two dimensions. The reflector is defined to be 10 wavelengths across, so electrically large to be sure. An f over d ratio of 1/2, so that's certainly within the reasonable range of f over d's. Focus fed and cosine squared. So there's our cosine squared, and we're using the traditional feed coordinate system. Here's our cylindrical wave. Now a line source in 3D is like a point source in 2D. We get a cylindrical wave. So e to the minus jk r sub f, the distance from the focus, divided by the square root of r sub f, as opposed to just r sub f, which is what it'd be for a spherical wave. And then we say for the region back here, there should be no radiation. So this is a very common cosine squared feed pattern. Now this is being analyzed as a two-dimensional problem, but that's a pretty good approximation to an electrically long reflector. So what we're doing here is we're simply assuming that if we were considering this as a three-dimensional antenna, then we're simply saying that to a good approximation, this distance here is much, much greater than this distance here. And then we can kind of ignore what happens at the edges in terms of trying to understand what happens in the plane of the parabola. Okay, derivation of the physical optics integral. The physical optics electric field is given, at least to a good approximation, in the far field as j omega times the magnetic vector potential. Magnetic vector potential, we can make the substitution, and we have this integral, which we've probably meddled with before, but this is simply using the two-dimensional formulation again. So we end up with minus j omega mu e to the minus jk rho, where rho is now the distance from the origin, wherever the feed is located, square root 8 pi jk rho. We integrate only over the lit surface, that's physical optics. We integrate over the physical optics currents. I'll say what those are in a moment. This is the far field phase factor. And then we integrate over the surface. In this case, it's a length because it's two dimensions. Here are the physical optics currents, simply 2n hat, that's the surface normal, cross h from the feed. And again, that's defined to be non-zero only over the lit surface. So we need to know h. H we can get from the plane wave relationship, right? 1 over the free space impedance, or the impedance of whatever media we're in, we'll assume free space. Direction of propagation cross electric field. That's the plane wave relationship that gives you h from E. And we already have an expression for E. We wrote it down on the previous slide. So we obtain this expression for h. We need an expression for the surface normal. That comes from the geometry of paraboloids. Here is the relevant expression. So now we simply need to plug these expressions back into JPO and then subsequently into the radiation integral. Here are the physical optic surface currents. Taking that cross product between the surface normal and the magnetic field gives us this. So here's the radiation integral. Here is the physical optics currents substituted into the radiation integral. I'm pulling out everything that doesn't depend on the integration, the variable of integration. Inside, everything depends on L, on the distance along the lit surface. So I've left all those expressions in there. We see that rho prime is r sub f in the geometry of the current problem. And dl is r sub f d theta f. Now the way to think about this is that distance along a circle, x, y, arc length along here is rho d phi. So this is just rho d phi in the current coordinate system geometry. And then finally, rearranging things one more time for convenience, we have this expression. Note that I like to combine factors of k, the wave number, with distances wherever possible. That makes the expressions functions of wavelength as opposed to frequency. So it's often easier to deal with in a frequency-independent way. That's just a preference, but it turns out to be convenient in many cases. And then finally, we need to know that r sub f from the geometry of paraboloids is given by this expression, and phi prime in this geometry is pi minus theta sub f. So I've gone relatively quickly through these expressions, but there's nothing complicated here, and you should certainly be able to work through this on your own and verify that these are correct. In any event, this is the integral that we need to do. My suggestion here would be simply to compute it numerically. I'm not aware that this has a closed form solution, although it might, but there's no need really to do that. Numerical integration suits just fine here. And here's the result. This is the far field pattern. This is E super S, that's the field scattered by the reflector. I'm not considering the additional field that we get directly from the the feed, say in this direction, because that's not part of the physical optics solution. And it's not really clear how you would introduce this in the physical optics solution. That's a topic for another lecture. Here I'm just considering what gets scattered by the reflector, not anything that comes directly from the feed. The horizontal axis is phi. Phi measured from this x-axis, and the x-axis is broadside to the reflector. So as we go from 0, 0 is the main beam, desired main beam pointing direction, 90 degrees, that's in the y-hat direction, and then 180 degrees, that's in the minus x-hat direction. So what we see is kind of what we expect. We see a main lobe, we see side lobes decreasing here, and then of course we see something goofy happen when we get back here. We see the field going up. And that's because physical optics is bogus back there, right? In order to get back here, the field needs to be scattered by the edges. And for that, you need diffraction. So there's no way that physical optics can get the right fields back here. It should do a good job out here, and it does, but does a terrible job back here. So summarizing that comment, we see physical optics is okay to use here for the main lobe and the first few side lobes. It's degraded in this region. It doesn't just fail, it just kind of gets steadily worse. And then by the time we get behind the reflector, it's garbage. It's not valid. So, some concluding remarks. How do you get the pattern in the degraded and garbage regions? Well, as I've implied here, you need diffraction. So the uniform geometrical theory of diffraction would be a great choice to use in that case. A topic for a future lecture. What's the pattern in the narrow plane? In other words, we've considered only the pattern in the plane of the parabola. What about the pattern in the plane in which the cylindrical reflector is long? Well, there you could use aperture theory, right? In other words, this looks like a rectangular aperture. It's being fed by a line source. By the way, you could also use line source theory. That would be good enough to tell you something about the pattern, the main lobe and the side lobe level. This concludes this lecture on cylindrical parabolic antenna, physical optics.